This video is on dividing algebraic terms, and it follows nicely from what we've just done, which is we have done some multiplying. So if I was to just look at a quick example of multiplying, if I was to take a squared and multiply it by a to the power of 5, that's where we looked at it in a long way, which is not the way hopefully you'll do it now, but we talked about the fact that a squared is a times a, and a to the power of 5 is a once, twice, 3, will I fit it in, 4, one more time, 5, just got there, which means we have a string of, let's see, 1, 2, 3, 4, 5, 6, 7. Okay. And of course, if we're talking about a multiplied by itself 7 times, that would just be a to the power of 7. Okay. Now, I don't want you to do it like that every time, but I think it's important you have that understanding. And we obviously concluded that you can do the quick method, which is to add the powers, and you will get the 7. So when we're multiplying, we're adding the powers. I hope that's gotten you thinking about what we do when we are dividing. So let's have a look at this first example here. We've got now a to the 5 divided by a squared, and that is exactly the same as writing it with a division sign. So please know they're equivalent questions, and you might prefer fraction form, you might prefer the division sign, but you should be able to work with both. So a to the 5 is 1, a times a, twice, 3 times, 4 times, 5 times, and a squared is a times a. And this is where we think back to our knowledge of fractions and the fact that we can cancel. So I can cancel if the terms are the same. I can cancel one from the denominator and one from the numerator. You can see I still have an a common to both the denominator and the numerator. So what I am left with after I cancel them, the a's go into each other exactly once. So I don't have to worry about those now. I'm left with a times a times a, which is a to the power of 3. I'm hoping, considering what happens when we multiply, what did we do to the powers to end up with 3? I'm hoping you can see that instead of adding the powers like we do with multiplying, we actually subtract the powers. And that's the rule that we're going to use. So if we make the example slightly more complex than before, we can add some coefficients, which is just the number at the front of each algebraic term. We know that 8 goes into 24 3 times, and we've just done this on the previous slide. That became a cubed. Okay, notice that the same question can be written like this. So same exact question, one uses a fraction bar, one uses a division sign. Let's have a look at some more complex examples. First we're going to always try and split things up, so I actually do signs first, then I do the rest of the coefficient, and then I look at the variables, just to break it down so it's not as much work on my brain all in one go. So we've got a negative in the numerator, and if there's no sign in the denominator, it's a positive. Negative and a positive makes a negative when we're dividing. 10 divided by 2, which is the yellow part, is 5. And now we're going to be doing the algebraic part where, because we're dividing, we subtract the denominators, we subtract the powers. We subtract the powers in these algebraic expressions over here. So we're going to be doing 20 minus 5. I don't know where I came up with that word from before. So we've got m to the 20, so it's like a string of m's 20 times, and then a string of m's on the bottom 5 times. So if we remove all 5 of these, we'd be taking 5 out of the top, so we would have m to the 15. So once again reminding you that when we divide, if the base is the same, and in this case there's my base of m, or the variable is the same, we can subtract the powers. This is one for you to do. You can pause the video, give it a go, and then watch my solution and check that we have the same answer. So once again, break things up into smaller bits. So we'll do the signs first, then the rest of the coefficient, and then the algebraic part. So 2 negatives, make a positive. 9 goes into 45, 5 times, And p to the power of 12 divided by p to the power of 3, well, that's where we subtract the powers and get p to the power of 6. All right, one more example. We've got minus, let me just check how many more examples. Oh, we got a couple more examples. I think this is just not supposed to be there. Let's get rid of that. So we are dividing here. And we've got, this is one of those questions actually where it's better off that you change the division sign instead of having it like that. I think it's much easier to see this question if you have a division bar. So know that whenever you have a division sign and you're thinking I'm struggling a little bit, a fraction might actually help you a bit more. So we've got minus 32 a to the 6b divided by minus 8ab. So I'm going to proceed exactly like I did before. Signs, rest of the coefficient, variables, and I might even color code the a parts and b. So 2 negatives make a positive. I don't have to write the plus, so I won't. 8 goes into 32 4 times. Now when I am dividing, I subtract the powers. If there is no power, it's an imaginary 1, so it's going to be a to the power of 6 divided by a to the power of 1 is a to the power of 5. And this is the reason why I put this example, is because of these b's here. If we have in fraction, when we did fractions in year 7, if we have 5 divided by 5, we would say 5 goes into itself exactly once. If I have 10 divided by 10, we'd say the same thing. 100 divided by 100, minus 20 divided by minus 20. But with b divided by b, students get a little bit confused. But b and this b here, they're exactly the same size. So this b will go into this b exactly once. They will cancel out, giving 1. Okay, so not that they cancel out to 0, which is what some students will say, it's that they're the same size, which means this b here will fit inside that b exactly one time. I don't need to write the ones. You can if you like to, but you don't need to. So I just leave it. I can just cancel them out. But I think it's quite important that you understand when you do the cancelling that you're cancelling them giving 1 rather than 0 or something else. So the final answer is 4a to the power of 5. All right, this last example, it's a little bit, I think it's year 8, but probably for the higher ability students. So we're going to cover it, and I'm hoping that some of you understand what I'm talking about. If you don't, just ask me again in class, and I can explain it. I'll explain to you why this example is different to the rest, because it looks similar to the ones we've already done. Let's just color code it. I've got minus, love my colors, got an F, and we have a G and a G squared. That makes it much easier for me. Negative and a positive makes a negative, and if you have a negative, it's really better that it goes in the numerator. We don't leave a minus sign in the denominator. Let's reduce 25 over 10. 5 goes into 25 5 times and into 10 twice. So we'll get 5 over 2. If you notice, there's only an F in the numerator. There's no F in the denominator. So that means I'll just leave that F. If there's nothing that this F can cancel with, it doesn't disappear. It stays exactly as it is. It's untouched. Now, this last bit with the G's is why I did this example. I want you to notice that we have a single G in the numerator. I'll just draw this out here. And we have G squared, which is G times G in the denominator. So we've been doing this cancelling where we say, okay, I can take that G, cancel it with a G in the denominator. So what I'm left with is I still have a G, and the mistake a lot of students make is they say that G is in the numerator, so they'll go and put that G here. Well, if we look, here's your numerator, here's your denominator. That G is not in the numerator, it's in the denominator. So that is a big mistake that students make. We're going to remove that G and make sure we put it in the right place, which is in the denominator. And that will happen when the power of the term is higher in the denominator. So you can see that power of 2 is higher than the power of the G in the numerator, which is just an imaginary 1 there. So because the 2 is higher than 1, you'll be left with more G's, but they'll be in the denominator. Now, this is another example for you to try. It's a little bit harder. My recommendation is that you turn this question into a fraction. I think that'll make it easier to do. I would pause the video, give it a go now, unless you're very confused, in which case keep watching. Pause the video, give it a go, and then compare your answer with me. So we've got minus 16 x squared y minus 36 x cubed y cubed. Color code everything. Color. I feel like I'm painting. Color. And color. Alright, so let's break it all down. Two negatives make a positive. The highest common factor of 16 and 36, well, I think that's 4. 8 can't go into 36. So 4 goes into 16 4 times, and 4 goes into 36 9 times. As you can see over here with the x squared and the x cubed, the higher power is in the denominator. So if I was to remove those x squareds, that means I'd have to take 2 out here as well, leaving me with just 1x. Over with the y's, I've got 1 over here, and here I have a string of 3. So if I remove that 1, then this string of 3 would become a string of 2. And notice where they are. They are in the denominator, not in the numerator. So I would also need a y squared in the denominator. So the final answer is 4 over 9xy squared. Feel free to rewatch the examples, ask a question, ask a friend in class, but just make sure you fully understand those examples because they do increase in how challenging they are. Complexity. They increase in complexity as the video goes along.